This is a video giving you some details on how to complete the most challenging parts of uh, this activity, collecting more evidence about acceleration. The objective here is to collect evidence to determine whether the acceleration of a car and or a passenger are constant during a crash. We've calculated average acceleration, but we don't yet have evidence to tell is this acceleration constant, or does the acceleration change during the crash? Is there a peak acceleration that's very different from the average value? So I have collected some data. I actually just made it up to show you what I'm dealing with here. So the first step for you is still to carefully collect position time data for the whole crash. I want to show you these other steps. Before I do want to point out this word carefully here is actually important. When we pull out our ruler, um, we're only given every tenth of a meter to measure. But let's say I'm trying to measure the position of the head of the passenger starting at 20 milliseconds. I want to try to get at least 2 decimal places on that position number. I shouldn't just write down 2.567. I want to try to do better than that. Maybe that's 2.71. Maybe I decide it's 2.72, but I want to get 2 decimal places on that, like measure to the nearest centimeter, even if you're not sure, because it's going to make your position data a lot clearer. Velocity graphs are difficult to make, and it'll make it even more difficult if your position data is super rough. So that's just a plug for making sure that your data is carefully collected, and do your best if it's not on the line exactly to decide what the nearest centimeter actually is. Notice for time measurements, you're using the milliseconds value over here, and then you're dividing that by 1,000 to get a value in seconds. This is just a matter of moving the decimal places. So 5 milliseconds becomes 0.005 seconds, or 20 milliseconds becomes 0.02 seconds. When you're done, you should have about 20 points in your table. I have 17, that's plenty. I want to show you this step down here. So starting from here, this is what my graph looks like. And just like this says, your position graph should look curved. So a single trend line on these points doesn't help us analyze the pattern. That trend line doesn't really tell us all that much. If we want to study acceleration, we need to build a velocity graph. Here's what this looks like. This is where it gets kind of tricky. To do this, you want to use the linear regression tool to calculate the slope of what's called a tangent line. The tangent line tells us the slope of a curved line at one specific point. So here's how we do it. Select 3 points using the checkbox on the left of the data table. I'm going to scroll back up to my data table. I'm going to actually click this check mark to unselect all the points. And then I'm just going to select 1, 2, 3 points to use for my tangent line. I look down here and I can tell the slope is just using these 3 points. All of these other points are totally ignored. So I can take this slope off of the equation and look at the graph to check that the line matches the slope of the curve. I did that, then write the slope calculated in the equation in the velocity column of the data table using the row for the middle t value. So this is the middle t value. This slope is showing me the slope at that point. So I'm going to take my middle t value and write negative 201 as my velocity here. And then I select the 3 next points. And I look down, I check, okay, does that match the trend, match the slope of the line? Yeah, it does. Looks like the slope hasn't changed. So I'll write 201 again. One more time. Okay, it looks like the slope is almost the same. It's a little different. So I'm going to write negative 200. Notice, though, once we get to the curved part of the graph, things become a little bit more interesting. The slope is changing more. And as this curve gets less and less steep, the tangent line will follow that curve. So check this out. The slope for this next time value is negative 197. Go on to the next one, and it has changed even more to negative 183. This has become negative 160. Now I want to stop to point out these are not real points from the video. There's no way that I could measure out to 10 meters. This ruler only goes up to like 3 meters. I chose these points to show you an example of constant acceleration, but your graph may not show constant acceleration. That's kind of the whole point. So I'm going to keep doing this just as an example, negative 140, but know that your data is going to look different from this. I wanted to show you an example so it's more straightforward for you to do it on your own. Once you get moving on this, it doesn't actually take very long. And we are looking to make sure every single time, does that trend line match the slope of the curved line at this specific point? It still looks like it does, so I'm good. I'll keep taking data here, negative 40 and negative 18. I want to actually zoom in on this right now to show you what we're talking about when we talk about a tangent line. The curved line changes slope. That's what it means to be a curved line. Whoopsie, I didn't actually select all the points. The curved line changes slope, but this tangent line shows us the slope at this specific point. That's the power of the tangent line because it tells us how fast the car is moving at that instant in time, at that clock reading value. So we get negative 5. And I got one more here. Looks like, all right, that's a slope of 0. So the car has stopped at this point. After you have calculated velocity for each point, which I did, those are these values, change the vertical axis on your graph from position to velocity. So the vertical axis is going to change to velocity, and I now have my velocity graph. Let me check it out. Oopsie. So these are my points. I can tell that the car is moving at a constant velocity, and then it decreases speed to 0 velocity. I need to then figure out what the slope of that line is. Velocity is the slope of a position graph, but acceleration is the slope of a velocity graph. This looks like, for this section here, I'm gonna turn on some of these points. For this section here, it looks like this could be pretty constant slope. Remember, acceleration is the slope of a velocity graph. If the slope is constant, that means constant acceleration. So this value tells me the acceleration. This is giving me a number in scientific notation, so I need to actually do some calculation there. I'm not going to bother doing that. Your number will be different, but actually, sure, why not? If I did 3.96 times 10 to the third, that would be moving the decimal place 3 times. So 1, 2, 3. That's 3,960 meters per second per second. That's a huge, huge, huge acceleration. This is like 400 Gs. That is not a reasonable value for this crash. But the reason for that is because I made up these numbers. You are going to find a different slope for your velocity graph, and that number, whether the acceleration is constant or not, will give you an idea of how quickly this car is accelerating during the crash. This last question, there's 2 more questions here. What is the acceleration of the passenger or the car for the points that you chose? Is this value positive or negative? That's worth thinking about. This slope is clearly positive. You may have assumed that positive acceleration means that something is increasing speed, but that is not the case. This hint is telling you careful. Decreasing speed does not necessarily mean negative acceleration. So one of the reasons why this graph is important is it helps us understand what positive or negative acceleration might actually mean. Last question here, make a claim about whether constant acceleration is a useful model to use in this example. Defend your claim by referring to details in your velocity graph. I would definitely say for my made-up example, constant acceleration is a useful model. The trend line goes through the points quite beautifully. If I look, is there a pattern in the velocity? It looks like the velocity is decreasing in magnitude by 20 meters per second approximately each row in the data table. So yeah, that makes me think that this is an example of constant acceleration, but yours might not be. The question is not, is it exactly constant? The question is constant acceleration a useful model? Are the points close enough to the line that it seems valid? Or are they all over the place? In which case we would say, yeah, constant acceleration definitely not useful here. So hopefully this helps you figure out how to complete step 1, step 2, step 3 in here. And if you have questions, as always, you can email me or get in touch with me some other way. Good luck and have fun with this.